conjugate for the square root. Switch the minus to be plus. Divide by t times the same thing. Now you need to square both. The good news is when you square the square root, it becomes clean. I'm guessing your problem comes from here when you try to square both. What you get is 6 plus t minus 6 minus t, but you should have put a parenthesis here because 6 minus t are together. Then when you FOIL everything out by distributing the negative, it should be minus 6 plus t. Together, they give you 2t on the top. That's where the t cancel each other. And realize the bottom is okay. So let's just plug in 0. For our class, feel free to stop here. But if you want to do things like that, it's totally fine. So I will take both. I will take either. Sounds good? Okay, so conjugate. Now for 14. Its limit, x goes to 2 minus this, 2 plus this. Okay. If we have something tricky, we need to figure out how to remove the bar. Your x become positive or negative, right? But for this case, it's easy because 2 is actually not a bad number. You plug in, you have 0 over 4, and you can just answer 0. Sounds good? The tricky one will be when you have something x goes to 0 and this, then you do face the choice of positive x and negative x. But for this case, it's 2, so no big deal. Cool. Yeah, other questions from the homework? I saw another hand. Yeah, Adam Zonik. I cannot hear you. Can I say it again?
Could you go over problem 12, please?
12, 2.3?
Yep, 2.3.
Awesome. All right. Limit x goes to negative 4 over 3, negative 6 minus 8, x plus 4 over 3. That's exactly what I'm talking about just now. That's a very good example. Okay, so the first thing you want to do is you plug in the number. You find it's 0 over 0. Therefore, you try to cancel something. Then you realize if you just factor out negative 6, you have x plus 4 over 3 on the top. You have x plus 4 over 3 on the bottom. You really want to go ahead and try to cancel this. Everything good so far? Cool. The only thing stop you from doing that is you have an absolute value. So let's remove the absolute value. Okay. This one is going to have two possibilities. It's either this. Let me see. It's either this. Or this. Both cases, you can start to cancel things. You have a number, negative 6, or you have a number 6. Okay. The problem is, which one should you take? Well, it really depends on is x bigger or less than negative 4 over 3. Okay. Then you can see this one works for your right limit. And this one works for your left limit. Do you follow what I wrote here? Okay, then you have the right limit is -6, the left limit is 6. Are they the same? No, then does not exist. The reason is because left and right limit are not the same. You have something look like this, 6, -6. Okay, so no limit. All right. Other questions? Okay. If no questions from the homework, and oh yeah. If no more questions, let's go ahead and try to solve the 2.5, the last thing we have. All right. Okay, so for 2.5, we were talking about continuity. Basically, we're saying this is continuous, not continuous. Jump. Okay, asymptote. These are easy, but then we realize, okay, for sine 1 over x, it's really hard for us to say something. Therefore, we go ahead and try to define continuity using limit. Then we figured, wow, this one can handle all the cases before, as well as the last case. Good. Then we try to give each one a name of the discontinuities. This is called a removable. This is called a jump. This is vertical asymptote, and this is called oscillation. It's in your notes. Okay. After that, we try to define, well, since we have a limit equals to the function, of course, we can talk about limit on the left and the right equals to the function. We define one-sided continuity. In this case, it's basically left and the right continuity. Finally, we were talking about continuities on an interval. Everything we have done before, it tells you it is continuous at x equal to a. But now what we want to say is a function is continuous on a interval. A, B. Okay. We talk about several things. Number one, we usually use AB as open interval. And then Adam raised a question after the class. Actually, it doesn't hurt if you use AB as a closed interval, as long as you're clear that when you say something is continuous here at the starting and ending, due to the nature of the ending points, you only have a right continuous or left continuous. But if you don't get confused, we can say they're continuous here, even though we should really say it's a right continuous here. Okay, so be careful there, but it's no big deal. The second thing is example. We say this one is continuous. Without saying which interval. That basically means it's continuous on its domain. If we don't say anything, we mean as long as it's defined, it's continuous. Okay. Then we have the following observation. Number one, this one is not continuous. Everywhere. Why? Because it fails at 0. You have a vertical asymptote. But this one is continuous. Everywhere in its domain. Okay, this is true. It's not everywhere because there's a number 0 which doesn't work. But if you're just concerning about the domain, then it is continuous everywhere. Okay. Now, when we don't say anything, we mean the second. We don't mean the first. Okay. Now this is where we left. Number 3, we talk about how do you show something is continuous on an interval. For example, show y equals x squared is continuous on 2, 3. It's really easy to show it's continuous at 2, at 3, at 2.5. But if you want to show it's at any point in 2, 3, how many points are there? Infinitely many. Therefore, this is not possible. I can do them one by one, but I could never finish. Sounds good? Okay, that's where we're left. We say this is not doable, okay? It doesn't mean that it's hard. It means we just need to repeat the same thing forever, which we cannot exhaust all the possibilities, even for such a small interval. Then we go and ask mathematicians, can you guys do this for us? And give us some quick hint or quick menu. Okay, so just keep in mind, we took it for granted. They did the work for us. But now we do have a quick menu. And that is through simple functions. Okay. Here we are again. Two things. First one, the building blocks. All simple functions are continuous on their domain. This is the truth, proved by mathematicians. If you still don't have it, try to make the list with me. Polynomial, rational, exponential, and a trig. Polynomial is x squared. Therefore, they give you something radical, which is square root. E to the x give you something log, and the trig give you something trig inverse. Through inverse functions, and remember, we only have 7. We already have 7 here. That means we exhausted all the possible list. These are called simple functions. Sounds good? From now on, where is tangent x continuous? You don't have to show it's continuous at pi, it's continuous at pi over 2, it's continuous at 0, continuous at 1, 3, 5. You don't have to do anything of that. You just need to find the domain. Once you find the domain, it's continuous on the domain. Therefore, tangent x we know x can be anything, but x cannot be n pi. Take it back, cannot be pi over 2 plus n pi. N is any integer. Therefore, y equals tangent x is continuous everywhere except for x equals this. Sounds good? Okay. So to find the interval of continuity, you just need to do the domain. That's it. Second, something look like this. Is it simple? No. But it's a combination of simple things. Just looking at it, I see this which I know the domain. I see this, which I know the domain. I see this, and I see this. Each one is simple. Sounds good? Therefore, we just need a way to combine them. That goes back to the familiar f plus g, f minus g, f times g, f divided by g, and f circle g. And the answer is quite simple. We have the law of continuities. Okay. If f, g are continuous, so is f plus g. So is f minus g. So is f times g. So is f divided by g, given g does not equal to 0. And finally, if f gx is continuous at x equal to a, and fx is continuous at ga, then f circle gx, which is defined by f gx, is continuous at x equal to a. Okay, we have 5 laws. It's a lot. Good news is continuity is defined by limit. Therefore, the law of continuity is defined by the law of limit. So you don't have to memorize a thing as long as you already know the rules for limit. Sounds good? Okay. Well, over. This basically says just find the domain. Okay. So number 1, all simple functions are continuous on their domain. Number 2, the laws can combine them as long as they're well defined. Together, it just tells you a simple fact: finding the interval of continuity is the same as finding the domain. Because once you find the domain, they're continuous on their domain according to factor 1. Sounds good? Let's try one example. Let's try a big, long example. And then we're all set. Y equals ln x plus sin x square root of x squared minus 4. Okay. Find where it is continuous. According to what we just find. Find the domain, period. Okay. Now, what do you have? You have ln x, sin x, and the square root of x squared minus 4. What's the domain of this? Everything. So no restriction. What's the domain of this? Try to recall the graph. Right? So the domain is everything that is bigger than 0. You cannot have anything negative this side. The graph looks like that. What's the domain of this? Well, it's a square root. That means the inside should be bigger or equal than 0. Otherwise, I cannot take square root of -1 and still get a real number. Not possible. Okay? That's all the single part. Now, how did you combine them together? Well, clearly on the top, you did f plus g, no restriction. And then you did f divided by g. Now you know in addition to the single part, you do have one additional requirement, that is g cannot equal to 0. That's from the limit law, the continuity law. Still okay? That means you start from bigger or equal, but now you should really erase that because equal is not an option anymore. That's all the restrictions about my domain. That's roughly the answer. Everything makes sense so far? The rest is try to combine the answer and simplify. This is already simple. X squared minus 4 bigger than 0. Use whatever you learned from college algebra to solve it. You want where is positive, so this one gives you x less than -2, and x is bigger than 2. Combine with x bigger than 0. Now we have this. Bigger than 2, less than -2, bigger than 0, and you want the intersection, you can see it's gonna be this part. So finally, together they give you, or you can say 2 to infinity, whichever way. And fx is continuous on 2 to infinity. The reason is because this is also the domain. Okay, take some time, read it. Some of you are quicker because you still remember the thing. Some of you may need some time. Raise any questions you may have. Yeah, Aaron.
So if this is pretty much just 2.5 is finding the domain and if it's continuous or not.
After all the build-up, yes. The final conclusion is, even though the new thing looks fancy, it's just found in the domain.
Okay.
Yep. The key thing here is your domain is where you are continuous. We established that fact. Therefore, they're the same. Anything else? All right. This will be the most difficult example you will see in the exam. So if you're totally okay with the thing I just had, which include a lot of domain finding and combination and solving inequalities, you will be fine. Okay. If you feel kind of shaky, especially how to get this, time to review for your college algebra. All right. One more thing, and the section is over. This one is called the intermediate value theorem. It's phrased as following. If fx is continuous on AB, close the interval. Okay. Fa does not equals Fb. Let n be any number between Fa and Fb. Then there exists a C in AB such that Fc equals n. Keywords: fx is continuous. N is between Fa, Fb. Conclusion: Fc equals n for some C in AB. Okay. What does it say? Let's draw a graph. Basically, what it says is you have an interval, A, starting point, and B, ending point. You have a function. One is bigger, one is smaller at the two ending points. Okay, so let's just assume Fa is smaller, Fb is bigger. Now what it says is you pick a number n, which is between Fa and Fb. So you pick some n in between. I'm just going to pick a random one. Okay. Then this one tells you if fx is continuous, then at somewhere from here all the way to here, your function value is exactly n, which means your function intersects this line at some point between A and B. Like this. Or actually, let's go with the easy one. That is where your C is. Makes sense to everybody from the graph? Okay, can you see that? You need something to be continuous. And can you see that there's guarantee you can find a C? There's no possibility that you went all the way from this point to this point. You did it continuously, but you didn't touch the horizontal line. It's not possible. You definitely touch it somewhere. That's what it says. Question, Jordan.
Yeah, so when you drew that graph before you erased it, what would happen then? So like if you had it hit the line twice, you know what I'm saying?
Yep.
Yeah.
Yes, right? Do you
Yeah.
have a C? Yes, and you have more than one.
Yeah.
So basically the theorem is just says you should intersect at least once, but maybe more.
Okay.
But you cannot do it without intersection. Cool. Okay. Other questions? Awesome. Let's try some examples to see. True or false? You were once exactly 3 feet tall. Use your button. If it's true, answer yes. If it's false, press no. Okay, Zachary Morgan. Yep, you answered yes. Can you tell us why you think it's yes?
Because obviously when I was born, I was less than 3 feet tall, and now
Hold
I'm
on.
tall. So at some
So
point, I would have.
born, you were less than 3.
Yep.
Okay, and now you were bigger than 3.
Yes.
Okay, so now if we put it here, you were born here, let's say 0, and here is now. You were less than 3, that means you're somewhere here, and 3 is above.
Yep.
You're bigger than 3, that means you're somewhere here, and 3 is in between. Can you see this is actually FA, this is actually FB. And basically what I'm trying to say is you were once exactly 3 feet tall. It means this one has to intersect with that. Can you see that's exactly the intermediate value theorem? And you assumed something which you didn't say, that is your growth is continuous. There's no way you can just, I'm 2 feet right now. You just blink your eyes, I'm 4 feet now. It's not possible, right? You have to go increment by increment. Great. Now let's think about basketball game. At the beginning, you score 0. At the end game, you score 70. I claim at some time during the match, during the game, you score exactly 59. True or false? Okay. Nick Peterson. You said no this time. Can you tell us why?
I mean, in basketball, you can score either 2-pointers or 3-pointers, so we really don't know. So it's not for certain. I mean,
So which condition did we fail? Because again, it's like when you were born, you were like 0 score. When when it's 70, that means you touch every single point in between by intermediate value theorem, right?
Yeah, but it's
why is
not
that?
Because it's not by one point.
Great. Okay. So you can see why we need continuous. Right? It's very possible you got a 58, you shoot a 2 or a 3, you got 60 or 61. So you skipped 59. The reason here is your score of basketball is not continuous. You could never score 59.3. You either got a 59 or 60. Sounds good? Okay, so we need those continuity. If you draw the graph this time, it's actually not hard to see. You start from here, you end here, but for basketball, your score go like this. Sometimes 3, sometimes 2. Okay. Now if I have n, I can certainly just jump through it without touching it because I fail the continuity. Okay, you can try to make up examples like this. From now on, it's just like, hey, yesterday was 36 degrees. Okay, now it's 70 degrees. I claim somewhere during midnight or maybe in the morning, it's exactly 44 degrees. It's exactly, I don't know, 55 degrees, or it's exactly 60.21 degrees. They're all valid. But you know that in order for that to happen, you have a very bold assumption, that is the temperature change continuously. Sounds good? All right. Okay. Later, we will introduce an advanced version for derivatives. That's something you can use to actually argue in the court with the cops, like, did you speed or not? But we will save the thing for that. Now, question. Here's an interesting application. Does everybody know how to solve this? Quadratic formula, right? Awesome. Does anybody know how to solve this? You would wish there is a cubic formula. Now here's the interesting thing. Is there a cubic formula? Did your teacher just didn't tell you there is something? Or actually there is no such thing? The good news is there is a cubic formula. We just think it's not so important. It's not so common to see it, so we didn't teach. There is also something for x to the fourth. And then you may think there's an x fifth. But then a long time ago, actually 800 years ago, a guy named Galois proved that there's no formula for equations with anything bigger than 5 degrees. That means, yes, you do have formulas. You may think there are all formulas because polynomials, they are just polynomials. They're easy, right? But the truth is, you couldn't solve anything which is bigger than 5 degrees. There's no such formula. We can prove that. Sounds good? How do you feel? You solved the equation for all your life. Turns out you couldn't do anything that is bigger than 5. That's pretty sad, right? But then you say, wait a second, but Wolfram can solve anything almost. Any complicated thing you type in, they can solve it. So how did they do it if there's no formula? Maybe there's another way to solve the equation without using a formula. Make sense so far? And let me show you how they solve it. This is not all the method they have. This is one way. And they use the intermediate value theorem. It's actually quite simple. You want to solve this, right? And you don't have a formula. Fine. What I'm going to do is I'm going to turn this one into a function. I'm going to try to find where fx equal to 0. That means solving the equation. Now this is what I'm going to do. I am going to start to guess the solution. I think the solution is 0. And you think I'm stupid. And you have all the reason of doing so because you must be really lucky if you can guess it. Okay, is it 0? No, then 0 is not a solution. Okay, now I'm going to guess 2. 8 minus 3, which is 5. So 2 is not a solution either. Now I'm going to guess 3. What should you say? Dr. Chen, stop. You know, you're not going anywhere. This is not going to work. Unless you learn something from this. Otherwise, you're just doing random guessing. And how rare is that you're going to guess something which is an integer? You don't even know it's an integer. Maybe the solution is 1.34. Are you going to guess 1.34? Okay, cool. But now wait a second. What did we just do? We have a function which we don't know the shape. We do know if we plug in 0, we have -1, which is not a solution. I agree. If we plug in 2, we do have 5, which is not 0. I agree. Good so far? Moreover, I know this is continuous. And what do you want to know? You want to know when fx equal to 0, which is between -1 and 5. When will my function hit this n, which is 0, which is in between this and this. Now try to recall if it's continuous, and your 0 is between fa, which is -1, and fb, which is +5, you are guaranteed somewhere you will have this solution. Does it make sense here? Okay, so even though the first thing, they're not the solutions, but then I successfully narrowed down. I don't know where the solution is, but it's here. It's between 0 and 2. That's very better than what we started with. We started with anything is possible. Now it's 0, 2 is possible. Sounds good? But this is not good enough. How do we make it better? Let's guess F1. Maybe 1 is a solution. Okay. Sad, it's not a solution. But we know it's here. Okay. Intermediate value theorem. Now, I think I narrow it further down to be 1, 2. Because 1 is positive, 1 is negative, somewhere in between, it's 0 exactly. Good so far? Is it better? Okay, can you make it even better? Let's try 3/2, which is right in the middle. Eight minus 8/12 minus 1, which is 8/8, which is 7/8, which is positive. Therefore, it's here for 3/2. What do you say? It's between 1 and 3/2. Okay. Better? Can I make it even better? Take the middle point. Between 1 and 1.5, that's 1.25. What can happen? 3 things. Number 1, f 1.25 is 0. Then you just got lucky. You found the solution is 1.25. Okay. Or f 1.25 is bigger than 0. Then you know at 1.25 it's bigger than 0. At 1 it's less than 0. We know it has to be this interval. Otherwise, if it's less than 0, and we know it's positive here, it's going to be the other half of the interval. Either way, it's going to be better than what we have here because this time the size just shrink by another factor of 2. Does it make sense here? Okay, so this is a very interesting procedure. Basically, you just take this one, you take this one, you take the one in the middle. Okay, make sure 1 is negative, 1 is positive. Depending on if this one is positive or negative, you know you should pick the left one or you should pick the right one and then repeat the process. Still okay? And every time you do this process, what happens? The interval becomes smaller. How much smaller? You shrink the interval by half every time. That means if you start with 0 to 2, you repeat this process for 100 times. Originally, how long is this interval? 2. You shrink it by half every single time. When you do it for 100 times, the interval is going to be 2 to the negative 99. I don't think I need to mention. This is something super, super close to 0. Make sense here? That means eventually you don't have the solution, but you do have an interval, which is something look like this. 1.11345 7 8 9 1.11345 8 8. It's still an interval, it's not the solution, but you can see the interval is so small that at least the first, I don't know, 1 2 3 4 5 6 7, the first 7 decimal is going to be accurate. Still okay? And do you want more decimals? Do it for 1,000 times. Then you're going to have something even better. The first maybe 20 digits agree. The only difference starts from the 21st place. Still okay? From here, we can see knowing no formula, just using intermediate value theorem. You can repeat a simple process by many times. You can get as close as you want to the real solution, even though you cannot get it right away through a formula. You cannot answer the answer is square root of 2. You don't have that. But you do have a very, very accurate decimal. And it becomes better the more you do. Make sense here? Okay, this method is called bisection method. The solution is technically not a solution. It's not the exact solution. It's actually an approximation. But man, it's a really good approximation. Still okay? How great is this? As long as your fx is continuous, this will work. That means you can solve this. As long as you make sure it's continuous, you can actually solve this one plus minus 3 equal to 0. Do you have a formula for that? I don't want to even bother. There's no formula. Okay? But you can repeat exactly the same thing as long as you can prove it's continuous somewhere and your solution lies there. Repeat the process. You can get the accuracy you want by doing more. Does everything make sense here? And of course, the beauty here is leave it for the computer. The computer will be able to run 1 million times within 1 second. So don't even care. Like after that, my thing will be this much accurate. 1 million. Do you know how small that number is? You can't tell the difference. It's basically 0. Okay. Good. Oh, Addie, questions?
Yep. Okay, so to use the bisection method, you need to first make sure that the function is continuous everywhere, right?
Otherwise, like the basketball, even though it's 0 and 70, there's no way you can know there's a 59 in between.
Right.
Right. So
Okay.
it has to be continuous. Good news is if it's not continuous,
Right.
we have some other method. This is just like the first elementary numerical method you will see. And people spend 100 years on this to solve all kinds of questions. Because this one, even though it looks nice, it's actually really slow.
Okay.
And this one doesn't work for high dimensions. For example, if you have a 3-dimensional thing, you try to see when is that thing touching the xy ground, which means you want to solve something fxy equal to 0.
Right.
Bisection method won't work, but something else will work.
Okay.
Great question. So there is a whole field called the numerical method, and that is my PhD work. All the idea there is use some mathematical tool to design a simple procedure, which we call algorithm. And then we run this through the computer. Then we get the approximation. For some well-defined problem, we can get as close as you want. For example, like 1,000 decimal accuracy within 1 second. For some harder problems, actually, it takes you forever to even get something workable. So it really depends on how hard the original problem is. And the people's intelligence focus on how to design better algorithms to run faster, okay, with a higher accuracy, which is more prone to uncertainties, and finally use fewer memory in computer science. So that's a whole field. Now, if you go to Wolfram, pay some respect. You know, even though they looks pretty stupid, they just give you the answer. Actually, there's a lot of brilliant ideas behind it. Okay, this guy made a company. I think Stephen Wolfram. Actually, if you guys are interested in him, you should check out the books he writes. Wolfram, Stephen. He's a crazy guy. He did a lot of amazing stuff, and he's very cocky. So as long as you get used to the style of his writing, it's just like I'm the best. You know, this is a big discovery. He's really smart, and he has a new way of doing science. Yeah, we have time, so let's talk about it really briefly. Right? How do you learn science? Well, you observe. You see the stars going around woo, 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 for a long time. You see the records, and suddenly, somehow your brain clicked. You figure out, wow, F equals ma. That's what Newton did. Sounds good? You see the phenomena, then you guess what's going on. When you see enough, you're smart enough, okay? You actually guess what's the underlying principle, and then you verify it. What he claimed is super interesting. You start with something super, super simple, okay? Then you let them interact each other with very simple rules. Simple building block, simple building rules, interacting rules. Good so far? Then it's almost like farming. You plant the seed. and then you let that thing grow in computer. Still okay? After a while, you can imagine those kind of simple thing grow to very complicated pattern. And those complicated pattern usually is meaningless. Still okay? But what if you use some simple rules, you let it grow, and it grows to something really similar to the real world? Then you know maybe that simple rule is what is underlying the real world phenomena. So this is almost like the other direction around. You don't observe, you just make. Until you see something you make is the same as the thing you see in the real life, but you already know how to make it because you made it from the beginning. Make sense here? So this is almost like farming science. So now you just need a lot of seed. You need a big land, which means a lot of computer. And just say, go there and give me 1 million patterns. I will go inside and try to see which patterns are meaningful. Sounds good? If you're interested in that, Google something called cellular. Oh shit, how do I spell it? Cellular, cell. Automata. Okay, that's the idea behind all this, which is super interesting. And he called it a new kind of science. You do by making and then recognizing compared to you observe and then try to guess, which is super, I don't know, it's almost hopeless now because things become so complicated. All the other ones has been done by Newton and Einstein. Okay, so now you see the phenomena because it's so complicated. There's so much detail involved. There's no way you can backtrack what happened at the very core. So why don't you just take the other direction around? That's his philosophy. Okay, cool. Class is over, and feel free to leave. I will stay here for questions if you have.